This talk is Defense Against Rapidly Morphing DDoS with Mikhail, Fedorov, and Mudit Tyagi. Guys?
Thank you. It's an honor to be here. Thank you very much for being with us. Let me just begin with the acknowledgement that young people, the younger generation, is very, very sharp. They're very smart. They've figured out how to take over IoT devices and make botnets. And they're selling DDoS services. This is an ad from Pastebin. And if you notice, for 10 bucks, you can get 500-second attacks with 60-second cooldowns, right? For 10 bucks. That's cheaper than pizza in New York City, and probably also here in Vegas, right? So all of us need to be ready to deal with DDoS attacks. What do you do to get ready? Well, we should be testing our DDoS posture, and we should be running red team, blue team games to make sure that we are absolutely prepared when DOS hits us, right? Now, if you get DDoS, who do you call? DOS busters. So I'm Mudit Tyagi, architect at F5 Networks, and that's how I used to look when I was younger.
My name is Mikhail Fedorov. I'm engineer at F5 Networks, and I had my hairs before I started to fight DOS attacks.
Yes, fighting DDoS, you lose your hair. So you now know who we are. How many of you, hands please, how many of you recognize this character? Okay, good. Now please help me out here. I'm a bit nervous, so help me out. Why is it so difficult to fight this guy? Why is it so hard to defend against Model T 1000? What's so special about him? Liquid. Liquid. He can change his form. He can morph. One moment he looks like a cop. Another moment he looks like Sarah Connor, right? And just when you think that you figured out all his shapes, he morphs again. He can even become a tile in a hallway, in a building, right? So very difficult to figure him out because he can just continuously keep morphing, right? Now this is exactly what happened to our friends at ProtonMail. In June 2018, they were hit by sustained DDoS attacks. The vectors that got used in these attacks, they were run-of-the-mill vectors. You know, UDP floods, Syn Floods, etc. Nothing too special about the vectors. But what made the attack so complex to defend against is that the attacker kept on changing the attack. They kept on morphing the attack, right? So as the SOC deftly would go and figure out what's a good mitigation for the attack and place that mitigation in mitigation mode in some device, the attackers would simply morph the attack, change the attack. So the mitigation that got placed in order to defend against the attack was no longer useful. Now, ProtonMail. We are huge fans of ProtonMail. We truly appreciate what they do for the community. So for us, for Misha and me, when ProtonMail got attacked, we took it as an attack on the community, on ourselves. And we said, all right, let's figure out how to defend against these attacks. What do we do to catch the morphing attacks and and defeat them, right? The other thing I would say about ProtonMail that we really, truly appreciate is that they were actually transparent about the nature of the attack. So researchers like us could actually study the attack and figure out ways to defend against it. Now, when you begin to research, the first thing we needed was a tool that could actually simulate morphing attacks. And so we looked around and we didn't find any good tools. So we had to write one. So Misha wrote a tool. Misha, you want to take it up and describe the tool you wrote?
Right, so we are sure that everyone in this audience is smart to write your own tool to launch Morphing Floods. But we decided to save you some time and wrote Soda. So Soda is able to launch DOS floods on the various levels, on the network level and application layer. It uses the existing tools to generate traffic, but scales them to the multiple cores in order to increase traffic volume. And of course, it allows you to morph attack pattern continuously. So SODA can be used in order to put down any part of your infrastructure. Firewall, application services, everything. So SODA is a tool for the red team.
Right, so SODA is a tool for the red team. For the blue team, what we did is we came up with an environment. We were just talking to Nathan, who's discussing with us that he has to do some DDoS testing, and doing DDoS testing can be complex because even DDoSing your dev environment touches your network, right? So you need a safe environment where you can do your testing against DDoS. So we put this together. And the blueprint that we show you here, you can use it as is, or you can customize it further. Now, let me explain the blueprint to you a little bit. So we've got clients which are running as Docker containers. You need those because you want to see what the end user's experience looks like when SODA begins to attack. And then on the very right-hand side, you've got the DAM vulnerable web application running in containers. That's the target. And then you've got pfSense, which is an open source firewall. We wanted to create an environment that looks like your network. So typically, you're defending the edge of your network with a firewall. So we picked an open source firewall. Now, all of these elements, the client containers, the DVWA containers, pfSense, they're all instrumented with Telegraph. If you don't know what Telegraph is, it can telegraph metrics whichever host it is instrumented on. So it's sending real-time metrics into InfluxDB, which is collecting these metrics, and then with Grafana we can show dashboards. You need all this because you want to be able to see what is happening to my clients, what is happening to my servers, and what is the state of my firewall as SODA attacks. So we put all this together. And now what you can do is stick your DDoS defensive mechanism just before the firewall. Keep in mind, a DDoS device is a default open device. Unlike a firewall, which is a default deny device, and you open a pinhole, DDoS device is a default open device. It's got the hardest job in the world. It's got to let everything through, right? Do not drop anything unless there's an attack, and then only drop the bad packets. And today, the biggest challenge that DDoS defense faces is there are often too many false positives. So what happens is people create, they use what we call static vectors and set thresholds for them. So for example, they'll say, I'll only allow 10,000, 20,000 UDP packets per second. My normal load is 10,000. My firewall can take 30,000. So I'm going to allow 20,000 UDP packets per second. When the attack comes, you might see 200,000 UDP packets per second, right? And you're going to have to drop most of those because you set a threshold at 20,000. So you're dropping 180,000 UDP packets. And the chances are that 10,000 good ones are part of those 180,000 that you're dropping. So you end up causing a lot of false positives. Now, the SOC analysts who are experienced, they know this. So what they do is, they have put systems in place and best practices in place. They look at packet captures and other indicators and try to find very specific characteristics of the attack packets, and then make a regular expression and program that in some mitigation device and try to be very specific about what they drop. But this takes time and doesn't work for morphing attacks. By the time you figure all this out, your mitigation is no longer useful because the attack is already morphed. So what we figured is, okay, a machine is coming at us. So we got to defend with a machine. So we investigated some machine learning algorithms. The algorithm that we tested, it baselines the traffic, and then when it detects an anomaly, it triggers on that anomaly, and it begins to mitigate. Whoa, careful. Because what if your marketing team does a massive, wonderful campaign and drives a whole bunch of new traffic to your site, and your infrastructure team does a great job and prepares for that new traffic, right? Nothing is going to go wrong. But the anomaly detector is going to see anomaly and start dropping. You don't want that. You just spent all this money driving traffic to your site, so you don't just want to drop because the anomaly detector is unhappy, right? Another example, you have a star developer, and your customers want a brand new feature, so she codes rapidly, checks it into GitHub, she then pushes it out through CI/CD, the code is in production, the application's nature has changed a little bit. Traffic patterns have changed a little bit. Whoa, the anomaly detector says attack, right? And you don't want that. You want your users to be able to use the new features. So what we discovered is that you need a second mechanism, a second machine learning mechanism, which is watching the state of the service. So is the service degraded or is the service doing well? That's what this second algorithm is watching. And it's supervising the first one. So if the end user experience is good, the service is doing well, it tells the anomaly detector, don't do anything. Just keep learning. And as soon as it sees that the service degrades, the end users are unhappy, then it tells the anomaly detector, find the anomaly, start the mitigation. And then it keeps on checking how effective is that mitigation. So if after mitigation is deployed, the service becomes better and better and better, the user experience goes back up to normal, it will say, great, we found the right signature. But if it sees that after application of the mitigation, the service is degrading even more, it's not helping, it will tell the anomaly detector, you found the wrong thing. Drop this one and look for another anomaly. So when you have these two things working together, you have the anomaly and proof of harm together. When these two things happen together, then there's a great chance that the two are correlated. We found this approach to be the most effective approach. Misha ran a lot of tests with Soda, and he's now going to discuss the results.
Thank you, Mudit. So the main goal of our experiments was to check how good machine learning at mitigation of Morphing DDoS floods. As you all know, there are two main victims in your network which can die when DOS floods come. It's your infrastructure and your application services. Your infrastructure usually dies when network level floods comes to the network and bring a huge amount of traffic. And your application services usually die when application layer attack comes. It's important to know that we've used two kinds of anomaly detection mechanisms in order to find the anomaly and stop it. And the main difference between them is subset of predicates they use in order to identify an anomaly and build the signature. The first one uses all available fields in the packet to build anomaly pattern. And the second one uses application payload, in our case it was HTTP, in order to extract predicates from and build the signature. The way we ran our experiments was there is attackers and clients on the left, then DOS protection device, then firewall, and then application services. And I would like to cover two experiments. First one, how does machine learning defense against network level floods? So this is a peacetime, and the user is happy. The latency jumps near zero. There is no attack traffic now, just 20 packets per second from attacker machine. Firewall doing well, it doesn't see much traffic because legitimate traffic usually much less than firewall can do. Backend CPUs are relaxed and they happily handle all legitimate requests which come to them. Then boom, Soda started to launch network level floods. And you can see that network attack pattern changes every 2 minutes. There is a Syn flood, UDP flood, NDP flood, and so on. And firewall CPU is so busy dropping this traffic, it is not even able to pass legitimate requests towards the backends. So backends don't see traffic at all. You see, there is amount of traffic is near zero. And this is complete disaster for a user. User barely able to access the service. This is a mostly outage. What do? We apply network level anomaly detection. What happens here is Soda keeps morphing an attack pattern. But now firewall CPU has enough power to handle all the traffic which comes to the firewall. So the backends are handling the same amount of legitimate traffic as they did before. And most interesting graph on this slide is the user latency graph. As you can see, at the beginning of every single interval, there is a small spike in the user latency. This is the only amount of time which machine learning takes in order to identify an anomaly and deploy mitigation. So few seconds. I believe it's an unreachable result for a human. Human cannot compete. Okay, this is a case with network level floods. What happens if application layer attacks come to the network? In this case, amount of traffic is much less than for network floods. And firewall easily handle all this traffic. But the backend CPU go crazy, they are overloaded. And the amount of requests is much more than we saw before. And this is also disaster for a user. So now latency jumps between 2 and 4 seconds. This is unacceptable quality of service. Now let's take a look. What if we leave only network level anomaly detection in charge? In this case, amount of legitimate requests which come to backends reduces. So backend CPU feels more relaxed. And from SOC operator point of view, everything becomes fine. But attacker is also happy. And the reason for that is user traffic is also affected. This happens because on the network level, good packets and bad packets too similar. There is no way to differentiate between them. So that's why network level anomaly detection generates false positives for application layer attacks. What do we do in this case? In this case, we can apply anomaly detection on the application layer to use application payload to extract predicates and build an anomaly pattern. If we do that, so Soda keeps morphing the application layer attack. But amount of, CPU cycles comes back to normal pretty quickly, just after a few seconds. The same about the amount of legitimate requests. And the user latency graph is exactly the same as we saw for network level floods. There is a small spike at the beginning of every interval, and it takes just few seconds for machine learning on application layer to detect an anomaly and stop it.
Excellent. So thank you, Misha. So I just want to point out to the audience in somewhat of a more animated fashion look, attacker attacks, I find the signature. Attacker attacks, I find the signature. Attacker attacks, I find the signature. Morph all you want, I'm going to catch you, right? So Misha, we now know that if the people in the audience use Soda and they can beat Soda, right? Their DDoS defensive mechanisms can beat Soda, they're doing well. But what is one piece of advice that you want to give to the audience? What do you want to remind them of? You know, an important point.
Of course, we have more than one piece of advice. So the first one is, so morphing DOS floods are now the case. ProtonMail case showed us. So we should check our DOS posture against morphing DOS floods. This is only how we can say we are protected.
Misha, we talked about layer 3, layer 4 attacks, layer 7 attacks, getting all mixed together and coming at you, right? So what should we remember to do in this case?
Right, so anomaly detection mechanism on the network level is not accurate enough to stop application layer attacks without creating false positives. So in order to block anomaly application layer attacks, you have to use anomaly detection on the application layer.
So Misha, anomaly detection can also cause false positives. What should we do about this issue?
Right, so traffic volume does not always mean an attack. So those devices should only go mitigate when there is a stress on your backend. So there is one more mechanism required to supervise anomaly detection. So Mudit, you've been doing DOS fighting for a while.
I've been.
What are best practices you would like to share with community?
Look, I would like to leave room for questions, but here's what I would want the audience to just memorize. When you think about DDoS attacks, you've got to focus on intelligent mitigation. The job of the DDoS device, if you look at the graphic there, red packets are bad, the blue packets are good. The job of the DDoS device is drop the red packets and let the blue packets go through. You cannot just say, I'm going to set a threshold and, and just only allow so many packets per second, because that mechanism is also going to drop the blue ones, right? So you got to be intelligent about your mitigation. And of course, you see there, the T1000 cannot hide the machine learning mechanisms. We can catch all his forms, right? But here's, if you can somehow, without dropping any packets, drive off the attack, that's the best policy. So the first thing we should try is just tell all the clients that are coming to your service, slow down a little bit. So each user is not going to feel that, but the collective impact of everybody slowing down could take some load off on the infrastructure in the back ends. Not easy to do, but theoretically speaking, that's the first thing we should attempt. Only after that fails should we get into the business of dropping. And when we drop, we should use these very precise signatures that the machine can figure out, so that only the bad packets are being dropped, right? And do it only when you have proof of harm, so that you don't cause false positives. And if you're still struggling, then you can start doing heavier things, like let the humans through, drop the bots, but be careful, because there's a lot of legitimate machine-to-machine communication nowadays, right? So if you break that, you might break your end user's experience. And after that, what you might think of doing is look at special connections that are indicative of attack. Slow connections. Someone might be hitting you with a variant of slow read, slow loris, etc., right? Or someone might be hitting your heavy URL, the URL that does a lot of computation in the back end. And when this doesn't work, now you drop the hammer. So now you start doing your rate limiting. Even this you have to do carefully. If you rate limit based on source IP, the most active source IP, careful, it could be a mega proxy. And you might be killing a lot of good users behind that mega proxy. If you rate limit your most heavily used URI, well, that's what people are coming to you for anyway. And finally, if you rate limit based on packets per second, well, there's no intelligence there. So really, you want to achieve intelligent mitigation, and your strategy should be something in that order. With this, I want to thank people who helped us out: Mark Campbell, Rachel, Sarah, and Lydia. They helped us practice and prepare for this. We want to take questions. And as we take questions, we want to tell you that you can download Soda. And here is Soda doing its magic. You see, the Soda is creating the attacks. This is a live demo. Well, we recorded it, so it's not live. It was live when we were recording it. Of Soda attacking and the machine learning catching the attack. So with that, questions. There are mics at the edge. This is the last session. So we're happy to stay here, but we don't want to keep you from your beer. Any questions? Question? Yes, sir.
Yeah, you guys didn't really discuss like which machine learning models you used.
Yes.
What you used for speed, and if you'll be open sourcing any of this. If you'll be open sourcing any of this code, or are you going to hold it back for your F5 products? Or, and how did you come up with the signatures for the attack?
Yes, yes. So the question is, we did not really discuss the machine learning models, which is true. But let me give you an idea of how they might work, right? So, and we don't want to really talk about products, we just want to talk about research. So the you can imagine at layer 3, layer 4, Misha mentioned layer 3, layer 4 predicates. So you can imagine, an IP packet, and it has all its, headers, options, source IP, dest IP, TTL, checksum, et cetera, et cetera. In the payload, you have your UDP datagram and your TCP datagram, and they have their own fields. So every single field that you can imagine that's present in this IP packet, TCP, UDP payload, it has a universe of possible values. So take TTL, 1 to 255, the easy one. So what we do is we're looking at all the packets that are coming in on the fly, and we see how many of them are TTL2, how many of them are TTL3. So we're building a frequency distribution, a histogram. Now, TTL is easy. What about source IP? So you have a lot of source IPs. So we hash them into segments, and then we build a histogram against each one, how many packets are hitting which segment, right? Keep in mind that we don't have the luxury of storing these packets and then running models on them. So our analysis is a lot more statistical. We have to do this in situ. As packets are flying through, we have to figure out, is the next one which we see good or bad? Is it anomaly or not anomaly, right? So we build these histograms during the baselining phase, and you need that second algorithm, which is, you can implement it using various techniques. You can say, I'm going to monitor my synthetic client's latency, and based on that, I'm going to declare, am I under attack or not? You can say, I'm going to monitor on the DDoS device what the round trip times are from the server. Is the server slowing down? And based on that, I'm going to declare whether I'm under attack or not. So there are different mechanisms, but you need it because in these statistical methods, you can have false positives. We will absolutely detect any change in the current network pattern compared to what we saw in the past. Absolutely, we will detect that. But is it a normal change or not? You need another mechanism to inform the anomaly detector to consider it an anomaly or just keep learning it. So we use statistical methods. We don't end up using the typical models that you run on data that you have the luxury to store. We got to do this in flight. And we're not going to open source the statistical methods. There are lots of papers. Yes, they may show up in products, etc. But we are absolutely open sourcing Soda, so you can download the kit. And also, our friend Ken is busily writing down as we speak here the instructions for putting together the rest of the lab environment. So you can test your DDoS mechanism, whatever it is. In your case, you'll still have the clients instrumented with Telegraph servers, the pfSense firewall. Stick your own DDoS device, and your own DDoS mechanism, and test. So all that we're going to open source. Any other questions?
I have one.
Yes.
So we've been talking a lot about layer 7 or application attacks. And early on, there was discussion about volumetric attacks, which are typically asymmetrical. So my question is where would the mitigation actually be placed in the network infrastructure?
Yeah, so that's a good question. So, and I can go on and on answering that question because you bring up several points, right? So if I'm seeing attacks that are stateful, right? So I'm seeing a request, I'm seeing a response going back. It's useful for me to see both the request and the response so that my mechanisms can be precise in discovering anomalies. And my mechanisms can be precise in discovering attack condition. You can do that at layer 7 and you can, or for HTTP, and you can also do that at layer 3 and layer 4 if you cannot see the HTTP traffic, if all you're allowed to see is layer 3, layer 4. Now, typically, if the DDoS defensive mechanism is placed at the edge of the network, you only see the layer 3, layer 4 predicates. You don't end up seeing the layer 7 predicates. And if the DDoS mechanism is also placed near the servers, often at the data centers, there's not a lot of depth in the network. You come to the edge and you go straight to your application servers. Then you will end up seeing the layer 7 predicates. If the traffic is asymmetric, the mechanisms will still work, but the precision of the signatures will go down a little bit. I want to show you, that's an example of a signature. That's a layer 3, layer 4 signature that you're seeing there. So you see we're looking at the IP header size flags, proto, source IP, TCP flags, dest IP, etc. And here's an example of a layer 7 signature, right? So you're seeing HTTP payload level information. So asymmetry makes the fidelity of the signature a little bit less strong, but the mechanism will still work, right? The math, the statistical model doesn't change, right? And typically you place the DDoS defense, if you're an enterprise, you get the ISP routers giving you a handoff to the enterprise routers, which then go to your firewall. You can be in between the ISP routers and the enterprise routers at the edge of the network. Or you could go just in front of the firewall, which is what I'm starting to recommend, because if you're just in front of the firewall, between the enterprise router and the firewall, you are more likely to see both the forward flow and the reverse flow of the session, because firewalls are often stateful.
Yeah, that makes sense for the application layer attacks, right? Can you hear me?
Yeah.
It makes sense for the application layer attacks to be close to the servers and, in fact, in front of the firewall. But for volumetric attacks, you'd still be overwhelming your
edge of the network.
your last mile from your provider edge router.
Yeah. Look, if the pipe is completely filled, right? If it's a volumetric, so volumetric attack, what does it contain? It contains a whole bunch of bad packets, right? And potentially, to really truly clarify, you can have a scale, a volume of the volumetric attack, which is so high that the pipe that you have from the service provider is just getting filled, right? And no, I can't fit another packet in there because the pipe is filled, right? So now my DDoS device, which is sitting right at the edge, what it's going to do is it's going to stop this traffic from making it into the enterprise, but it can't do anything about the pipe. The pipe comes before the DDoS device. So in this case, what you have to do is call a cloud scrubber and have the ISP transfer your traffic to the cloud scrubber so that you get appropriate amount of volume that your pipe can handle. Now, if the case is slightly different, where the pipe is not completely filled, so your pipe can still take another few gigs, but the volume of traffic is much larger than normally what you used to see. I can handle that on premises. Now this device, one of the examples we just showed you is the layer 3, layer 4 signatures. So in that volume, I don't need to look inside the payload. I will figure out what the bad packets are just by looking at the layer 3, layer 4 predicates.
Got it. Thank you.
Yeah, but thank you for asking the question. And I think, there's more question. Yeah, hi.
So the story that you guys have told here is really compelling. I've heard it from some DDoS defense appliance vendors. Have you guys done any kind of bake-off in your lab to look at performance for your solution versus their solution? I mean, I know you guys are still in sort of research and exploration and that sort of thing. So, but just curious to hear if there's any anecdotes about how you're doing versus what you might see on like a Defense Pro, for example. No, we haven't done any bake-offs. But you now have Soda. You do the bake-off, right? We'll help you set up Soda. Look, we don't care what you use. ProtonMail got attacked, and we got really charged, right? And we want the community to be able to defend against these types of attacks. And the strategies that I showed you regarding intelligent mitigation, they don't change. Whatever vendor you use, you write your own code, that's fine too. But focus on intelligent mitigation.
A. B, test your posture. And we understand that testing your posture is difficult, therefore we give you the kit. Use the kit, test your posture in a safe environment. And then, if we can help you, happy to help you as researchers, right? And if you want to call the vendors, go ahead and call them. But if you want to call Mikhail and Mudit, let's flash call us there. Oh yeah, it's my F5 email. So hit us on GitHub, right? Hit us on GitHub.
Sounds good. Thanks, guys. I probably will do
Let me
that.
also add, so the idea behind open sourcing the soda, that we will have a tool, the standard tool to test the DOS protection. So everyone will do the same tests. And this is how we can compare who is doing good, who is doing bad. So that's the idea behind the soda.
Sounds good. Thanks, guys.
Other questions? I think that we're supposed to.
Yeah, we're way over. There's going to be a wrap room over there for additional questions.
Yeah, we're going to go to the wrap room and drink our water and take a sigh of relief. And so, happy to answer questions there. Thank you, and thank you for letting us go.